three survivors. All right. So we're going to look at the interaction between the Dirac field and the electromagnetic field. Yes, this is all right like that. Okay, so far we have a Lagrangian density. Let's just call it the Dirac Lagrangian plus the electromagnetic Lagrangian. So this is the free Dirac Lagrangian density. I don't need to write that it's a Lagrangian density, you know that. So that's for the free Dirac field, and this is for the free electromagnetic field. So what we're going to add so the total Lagrangian density is going to be the free Dirac Lagrangian density plus the free electromagnetic Lagrangian density plus an interaction term. So you know what the free Dirac and free electromagnetic Lagrangian densities are. The interaction term, so in fact maybe we can just write, so let's write it all out. So the free Dirac Lagrangian density is write it like this: psi bar I gamma mu d mu minus m psi minus a half d mu a mu d mu a mu. All right, so far this is just the free Dirac Lagrangian density. And here we have the free electromagnetic Lagrangian density written in this Fermi form that's automatically in the Lorentz gauge, plus the interaction term. What is the interaction term? Here it is. It is E psi bar gamma mu a mu psi. That is the interaction term. Now, you could just postulate that. Say, here's the interaction term, and we find that it agrees with experiment and so on, and no problem. But one can also justify this term. Getting on my nerves. Let's see. What is wrong with this thing? For God's sake. Or anyway, you can see. All right. Okay, you can see. Okay, so justification. So you maybe recall in elementary quantum mechanics, if I have a charged particle in an external electromagnetic field, you may remember that in the Schrödinger equation, you make the following replacements. I d by dt is replaced by I d by dt plus E phi. So here I'm taking the charge is minus E. And we have an external electromagnetic field with a vector potential A and a scalar potential phi. So these replacements here, minus I grad is replaced by minus I grad plus EA. We make these replacements in the Schrödinger equation, and you get the Schrödinger equation for a charge in an external electromagnetic field. Okay, now what you could do is you could rewrite this as if I write my vector potential as write these the other way around. Time component first. Phi A. I can write it like this. I can say that the derivative with respect to x mu is replaced by something, let's call it a capital D mu, which is equal to d mu minus IE A mu. And this is often called a covariant derivative. And the reason it's called a covariant derivative well, let me just, I'll come to that. Okay, so now what we can do is postulate or assume same substitution. In the Dirac equation. So if you're asking, well, what is the Dirac equation in the presence of an electromagnetic field? So if in the Dirac equation I replace this derivative by this derivative, I add this term, what you find, the Dirac equation becomes I gamma mu d mu minus m psi equals minus E gamma mu A mu psi. Okay, so normally this would be equal to 0. That's the Dirac equation with that equal to 0. If I replace d mu by this term, I pick up this extra term. This is the Dirac equation in the presence of an electromagnetic field. Also, what happens to the Lagrangian density of the Dirac field? This is the Lagrangian density of the Dirac field. If I replace this d mu by that capital D mu, the Lagrangian density becomes, let's write it as psi bar I gamma mu d mu. Sorry. Lagrangian density of the Dirac field is replaced by this quantity here, which is just the Lagrangian density of the Dirac field plus our term here. Okay, so if you want to see, so in other words, what I'm saying to you, if you want a nice way of seeing, well, where does this term come from? Why is this the interaction Lagrangian? Okay, a simple way to see it is to say, well, if I take the Lagrangian density for the free Dirac field, and I make this replacement, I let d mu become d mu. Then then the Lagrangian density looks like this, and if I write d mu is equal to this here, I pick up an extra term. I get the free Dirac-Lagrangian density we started with plus this extra piece. Okay, so this is where this term comes from. Or at least that's one way of looking at it, but it comes from this substitution here. This is sometimes often called the minimal substitution. Now there's an important property that I should tell you. Let's up here. Is gauge invariance. So gauge invariance. So gauge transformations. You know that we have to change. So in the gauge transformation of the electromagnetic field, the vector potential is replaced by a new vector potential which is equal to the old one plus the gradient of a scalar function. Now, in order to make the theory total L want the total Lagrangian density to be gauge invariant, we also have to transform the Dirac field. Now you may remember something like this when you did the Schrödinger equation in an external electromagnetic field. You may have done this with something comparable, where you say, well, if I do a gauge transformation of the external electromagnetic field, you find that you have to also transform the wave function. There's a gauge transformation of the wave function. Here there's a gauge transformation for the Dirac field, which is the following. That the Dirac field is replaced by a new Dirac field, which is equal to the old one, multiplied by e to the I EF. And of course, you're not confused between E and E. Here E is 2.718, blah, 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 and here E is a charge on the electron. So, you know, what you do, some funny notation. Anyway, so, and of course, if you like, psi bar is replaced by psi bar prime, which is psi bar e to the minus I E F. Okay, so now we have a homework problem. Homework problem is to show. Homework is for you to verify this. So homework. So we have the total Lagrangian density is the Dirac Lagrangian plus the electromagnetic Lagrangian plus the interaction term. Homework. Show that let's see. Show that. So under a gauge transformation of A mu and psi. So we're performing this gauge transformation of A mu and psi. Show that these Lagrangian densities, how do they transform? So show that the Lagrangian density for the Dirac field, so hang on, I just skipped it. Okay. So let's look at the Lagrangian density for the Dirac field, and here's this, and see what happens to it if I transform psi by that gauge transformation. You should be able to show that it becomes, the new Lagrangian density is equal to the old one minus E psi bar gamma mu psi d mu f. Furthermore, the Lagrangian density of the electromagnetic field, well, we know this already, but you might want to check it. The Lagrangian density for the electromagnetic field doesn't change. It's already in gauge invariant. Okay, so notice the Lagrangian density of the Dirac field for the free Dirac field by itself is not gauge invariant. Okay, you change psi, you get an extra term. This piece is gauge invariant. So this is LP, this is LEM. Okay, and so now let's finally, what happens to the interaction term? I perform a gauge transformation on A and psi simultaneously. What happens to the interaction term? You should be able to show that it becomes, the new interaction term is equal to the old one plus E psi bar gamma mu psi d mu f. In other words, the total Lagrangian density is gauge invariant. Okay, the Dirac part picks up a term minus E psi bar blah blah blah. The electromagnetic part stays the same. The interaction part picks up a piece plus E psi bar blah blah blah, and of course these two pieces cancel. These two pieces cancel, so the total Lagrangian density is gauge invariant. Now this kind of thing is this is your first look at a gauge theory. This is a gauge theory of the electromagnetic interaction. This idea of gauge invariance is very important in high energy physics, quantum field theory, theory of particle physics. This is what we think of as the most fundamental way of looking at the nature of the electromagnetic interaction in modern physics. That it is an expression, or it is fundamentally related to this gauge invariant, gauge symmetry. This kind of idea has been extended to other interactions, the electroweak theory, the strong interactions. They're all described by gauge theories. The quantum field theory of strong interactions involve, it's a bit like this, but just more complicated. There are extra terms. It's a sort of more complicated version of this gauge symmetry, but it is a gauge symmetry. And this is how you derive the expressions for the interactions in the what's called quantum chromodynamics and so on and so forth. So this is sort of prototype for a modern understanding of interactions in high energy physics. So there we go. So we've, as I said, you could just postulate this. At the end of the day, this is the interaction term. Okay. So let's move on. All right. So moving on. We want to discuss the interaction between the Dirac field and the electromagnetic field with this interaction here. So, here is what we do. So you'll remember way back we discussed the interaction between an atom and the electromagnetic field. now we're discussing the interaction between the Dirac field and the electromagnetic field. So, first of all, I should say that in the quantum field theory, I've been writing these as if they're classical quantities. Let's now take all of these to be operators. And we do our usual, where the these quantities are replaced by the normal ordered. So this is not going to look very nice, but anyway, these are now all operators. And here we have normal orderings. These are operators. And let me at least write the last term out nicely. The interaction term is the normally ordered E psi bar gamma mu A mu psi, where these are operator fields. And this is the operator version of the interaction Lagrangian. Okay, so remember that the Hamiltonian operator in general is, well, let me just write the Hamiltonian integrator of Lagrangian density, which is, for a general set of fields, is pi r phi r dot minus L. Okay, I'm summing over the canonical momentum, the time derivatives of fields, minus the Lagrangian density. So, if I add a term like this, to the Lagrangian density, notice this does not depend on L interaction contains no time derivatives. It just contains the fields themselves and no derivatives of the fields. It contains no time derivatives. Therefore, the canonical momentum densities are as before. So what I mean is, for example, e.g., if I look at the partial derivative of the Lagrangian density with respect to psi dot, this is just the same as what we had before with just the Lagrangian density. The interaction term doesn't depend on psi dot. Okay. So the canonical momentum densities are the same as before. Therefore, so if we ask, okay, let me just, so the addition of this term, so the point is, adding this term to the Lagrangian density, what happens to the Hamiltonian? So the Hamiltonian is changed write it like this, adding this term to the, if I add this interaction term to the Lagrangian density, it means we add a term to the Hamiltonian, or sorry, a term hi equals minus Li to the Hamiltonian density. Sorry, this is what I wanted to say. Okay, I'm just saying something quite simple. That we're adding a term to the Lagrangian density. The question is, how does that affect the Hamiltonian? Because we want to find the interaction Hamiltonian. Now, if you look at the Hamiltonian, the expression, well, it depends on the canonical momenta and on the Lagrangian. The canonical momenta are the same as they were before. Adding a term like this that does not depend on derivatives does not change the canonical momentum. So these are the same as before. The only term that changes is this. So if we add a term Li to the Lagrangian density, then obviously we add a term minus Li to the Hamiltonian density. Therefore, so our interaction Hamiltonian is okay, this is our interaction Hamiltonian, which I can write as, if we let's now write as an operator, okay, because we're going straight to the quantized theory. So what is this? Our interaction Hamiltonian is minus the integral over all space of the normal product of E psi bar gamma mu A mu psi. Okay, of course these are operators. So this is our interaction Hamiltonian. And so it's getting exciting. So you remember CF before, remember way back when we were doing the interaction between an atom and the electromagnetic field, we had something like minus d dot E, where E was the electric field and D was the dipole moment operator for the atom. So it's that kind of thing. Here the interaction term, here's the electromagnetic field operator, and here's the Dirac field appearing in here. This is our interaction Hamiltonian. All right, so now we can forget about the Lagrangians and just think now in terms of the Hamiltonian. So we have our total Hamiltonian is equal to the Dirac Hamiltonian that you know all about, plus the electromagnetic Hamiltonian, which you know all about, plus this new term, which you're going to learn to know and love. All right. So now, here is something. We did this already in the case of electric field interacting with an atom, but let's just think about this a bit more carefully, is to study this with the interaction, we're going to use the interaction picture. Now the interaction picture, you may or may not have used it before. You can go through the derivation, if you like, I think in the appendix to the first chapter, there's something about the interaction picture. You'll find it in any standard textbook. I'm just going to tell you what the results are. The results are very simple. So in the interaction picture, so let's write this as the free Hamiltonian plus the interaction Hamiltonian. So the free part is, of course, the sum of the free Dirac plus the free electromagnetic field. Okay, but this is the free Hamiltonian that we've looked at so far, just the sum of the free Dirac and electromagnetic Hamiltonians plus an interaction part. So in the interaction picture is intermediate between the Heisenberg and Schrödinger pictures. So operators, omega, general operators omega, evolve via the free Hamiltonian only. Okay, just the free Hamiltonian. Whereas the states psi, in fact, seeing as the book calls it capital Phi. Let's call it capital Phi. State vectors Phi evolve via the interaction Hamiltonian only. So in other words, operators evolve according to the usual Heisenberg equation of motion, but where the Hamiltonian that appears in here is just the free part. Okay. Whereas states evolve according to a Schrödinger equation where the Hamiltonian that appears in here is just the interaction part. Now, let's just look for a moment at the first statement. So the operators evolve via the free part only. This implies everything we've learned so far stays the same. All our results about our field operators remain as before. As before. So in other words, so the same equations of motion, the same field equations. So this is a funny thing here. I'll get this straight in your minds. Even though the Dirac field, the electromagnetic field are interacting, the operator fields only evolve according to the free Hamiltonian. So in other words, as far as the operator fields are concerned, there's no interaction. So in other words, psi still obeys the free Dirac equation, and A still obeys the free electromagnetic wave equation. So the same free field equation. So that sounds a bit weird. Make sure you've got this straight. But hang on, the total Hamiltonian is the free Hamiltonian plus an interaction part. But if we take the interaction picture, the operators evolve only according to the free part. So if you work out, well, what is the time dependence of the electromagnetic field operator? It's just going to obey the free field equation, the wave equation that we had before. Okay, so it's the same free field equations. So we have the same expansions, the same field expansions in plane waves. So, A mu is like the sum of A plus A dagger, etc. All of that is exactly the same as before, plus the same commutation relations. Same commutation relations. And note, the canonical momenta are the same. The fact that there's interaction term, because the interaction term has no derivatives, the canonical momenta are the same as before. So in other words, the momentum conjugate to psi is the same as it was before. Nothing changes. So same fields, the same free field equation. So in other words, let me emphasize, get rid of this. So as before, I worked out, if I take the Heisenberg equation of motion and I apply it to the Dirac field, I'm going to get the free Dirac wave equation exactly as before, because there's no interaction. The Hamiltonian is the same as it was before. Okay? If I work out what's the equation of motion for the electromagnetic field operator, well, again, the Hamiltonian is just the same free Hamiltonian I had before. They'll get the same free wave equation. So I'm going to repeat this one last time. Even though psi and A are interacting, in the interaction picture, the actual field operators obey the same free field equations as before. Okay? So this is fantastic. It means that because we've been studying the expansions, we've written this as the solutions of plane waves, we've studied all their properties, all of that is carried over intact. Nothing changes. Okay? So in other words, basically, I can summarize it like this. Everything you know about psi A stays the same. They are, in effect, free fields. Okay? The operator fields are still free. So nothing changes. Fantastic. All right, so we don't have to go back and rework everything. We've got this interaction term. No. Everything. Commutation relations, field expansions, plane waves, same free field equation. The Dirac operator field obeys the free Dirac equation. The electromagnetic operator field obeys the free field equation. All right, I've said that about 20 times. That's enough. Good. So what's the new part? The new part is this here. This is the new part. Before we were in the Heisenberg picture, the state was static. So you can think of it like this. Okay, to go back to what we had before, if we set the interaction term equal to 0, if we ignore the interaction term, well then this is 0, the state is static. And so we have the same as we had before. We have the free field equations for the operators, and the quantum state is static. Now, though, we're going to include the interaction term, so the quantum state evolves in time. By this equation here. And there's something to point out where the final important point to clarify the interaction picture. So we have an expression for the interaction Hamiltonian, which is given by minus the integral over all space of the normal product of E psi bar gamma mu A mu psi. Check I've got this right. Alright, well these are field operators. Now, important point to get clear conceptually where this here is written. You may think, okay, this is our Schrödinger equation, this is our equation for the time evolution of the quantum state. This interaction Hamiltonian is expressed in terms of psi and A mu, where psi and A mu where psi and A mu are just the free operator fields that we've already worked with. Okay, so the interaction Hamiltonian is written in terms of the time-dependent free field operators, psi hat, A hat. Sorry if I'm making it sound more complicated than it is. Just want to make sure you got this absolutely clear. So when you write down this equation for the time evolution of the quantum state, the operators that appear in here, the psi hat operator, the A hat operator, are the free field operators that we've already worked with. Okay? So if you want to know what this looks like, remember A mu is a sum over plane waves with an A hat dagger, etc. Similarly, I can write psi in terms of C plus D dagger. Okay, in other words, the expansions that we did for the Dirac field, for the electromagnetic field, all get substituted in here exactly as they were before. They're just the expansions. Because why? Because psi and A mu, these operator fields, obey the free field equations. Okay? So this implies the same plane wave expansions as before. Okay? So this is beautiful because it means there's a great beauty of the interaction picture. It means that, well, to write down the interaction term, we express it, it's expressed in terms of the field operators, but the field operators have exactly the same plane wave expansions as before. They're the same free field operators. So we already have all of those expansions, so we can substitute in here and find and write the interaction term. So it implies can write the interaction term in terms of A hat dagger, C hat, D hat, etc. Okay, where what are A hat, C, D? These are creation and annihilation operators for photons, electrons, positrons, etc. Okay, so there we go. So once we have that formalism clear in our heads, then everything is going to work out nicely. So let's see. Okay. All right. So now it's really essential that if you've got all this clear, then not everything else is now just going to follow. We're going to substitute in the expansions that we had before. We're going to put in here, and we write the interaction Hamiltonian in terms of creation and annihilation operators for photons, electrons, positrons, and now it's just a matter of calculating matrix elements, and we can calculate whatever we want to calculate. But just to make sure, are there any questions about this? Any questions about this? It's important you get this clear in your minds. So nothing about the field operators changes. Okay, good. If anyone does have any issues, please please email me for an office hour. Okay, fantastic. So now what we're going to do is we're going to solve for the time dependence of the quantum state by a perturbation. We could treat this as a small perturbation. So, wondering if we ought to. Okay, so I tell you what we're going to do is I'm going to do it first. Solve with the initial condition. So we can take the initial condition that phi infinity. So of course phi depends on time. Okay, the state vector depends on time. We're going to assume that in the distant past, at t is minus infinity, it is equal to some initial state. So of course infinity is an abstraction, we just mean a very large time. So it's some very large time in the remote past. So the kind of situation you may think of, if I have, for instance, particles scattering in an accelerator, I have a beam of particles coming from far away, particles coming from far away, and they meet and they're going to collide. So these particles coming from far away, we imagine we have a state for these particles defined at t is minus infinity. But there's some initial state. And what we want to calculate is the final state by infinity just explain what this is. The final state at t is plus infinity. These particles collide, they scatter, and then they move off, and there are some detectors far away that detect where these particles are, what particles were created. We take that to be a very large time. So we've got particles coming in from far away, they're scattering, and they're moving out far away. So we treat this as some initial state at t is minus infinity, and then the final quantum state at plus infinity is given by an expression of this form where S hat is the unitary evolution operator, which you may have seen is often written as U hat. From the unitary evolution operator from t is minus infinity to t is plus infinity. In this context, instead of u, in ordinary quantum mechanics, you'll be used to seeing this expression that psi of t is equal to the unitary operator acting on the initial state. In this context, it's called S, and in fact, this is often called the S matrix. The S matrix operator. Just a terminology. I think actually the terminology S probably comes from scattering, the scattering operator, because you tend to be interested in scattering processes from minus infinity to plus infinity. But it is just your unitary evolution operator applied over an infinite time. So, and what we're interested in is the probability. What is the probability that the initial state makes a transition to a final state, F? This probability is given by just this quantity here. So I take the final state at t is plus infinity, take the inner product with F and the modulus squared. Okay, so I'm just saying this is the quantum state at large times. What is the inner product of that state with this state that I'm interested in? This is the probability of making a transition from the initial to the final state. So this can be written as just so in other words, it's just the modulus squared of this matrix element. So we're interested. So in order to calculate the probabilities, so the probability of a transition from an initial state to a final state is given by this. So in other words, if I prepare the system in this initial state that t is minus infinity. I let it evolve. And then in the far future, I measure the system to see what particles are present, what are their momenta. And I ask, what is the probability that the state I find is equal to f? It is just given by this quantity here. So we need to calculate matrix elements of the S matrix operator, okay, to calculate probabilities of any processes that we're interested in. So the initial and final states can contain different kinds of particles, contain particles or the same particles with different momenta, different spins, whatever kind of process you're interested in, you can try to calculate. So what I'm going to do is just begin with a simple, just to first order. Let me first write. We can first note that we can write the following. This expression here, if you take the time derivative, you get the Schrödinger equation. Okay, if I take the time derivative, this is constant. Here I get a derivative of, I get minus I times h acting on phi. So this implies I phi by dt. Okay, you should be able to show that straightforwardly. Here is the state at time t1. I act on it with the Hamiltonian interaction, Hamiltonian at time t1. I integrate with respect to t1 from minus infinity to t. With this factor plus this, that gives me the state at time t. Notice this is the state at time t, this is the state at time t1. It's just this is a useful point of departure for a perturbation series. You take the time derivative, you recover the Schrödinger equation. And it also implies that the state at minus infinity is equal to I. If I let t go to minus infinity here, then in this integral, if t goes to minus infinity, well then this integral will vanish. And so in other words, the nice thing about this, it's a compact way of writing the Schrödinger equation and the initial condition. We want to solve the Schrödinger equation with this initial condition. So what we can say is, okay, we need to solve this integral equation. Okay, so we need to solve this. And we do it iteratively. So what does that mean is, so to first order, let's just look to first order, and then we'll continue with the expansion next time. But to first order, so in the right-hand side, insert phi T1 is just equal to I. So the idea here is we're treating the interaction Hamiltonian as small. Okay, the interaction Hamiltonian is regarded as small. So in other words, we're thinking that, well, this term here is small. This term in here, this is small. So what I can imagine here is that the quantum state to 0th order, quantum state to 0th order is equal to its initial value plus small corrections. Plus small corrections. So I can say, okay, to find these corrections, what I will do, on the right-hand side, as a first approximation, let me ignore the corrections and just say that the quantum state is just equal to the initial value with no corrections. Okay. So what happens? I then get an expression for the corrected state. I find that 5t is then equal to I plus minus I integral from minus infinity t dt1 interaction t1 acting on I. So here, this was not really an expression for phi, because I've got phi here and phi under the integral sign. Okay, it's an integral equation. But now I have a first order expression for the quantum state at time t is equal to the initial state plus minus I, the integral from minus infinity to t with respect to t1 of the interaction Hamiltonian acting on the initial state. So in other words, so this is the correction. This term here is the first order correction to the evolving quantum state. So now, let's say we have the following. So one can then continue the iteration by saying, well, let's take the corrected quantum state and insert the corrected quantum state into the right-hand side here and obtain the second order and then the third order. We're going to look at that next time. You get a series of perturbations. For the moment, let's just look at the lowest order term. So what we have, we can write that infinity is equal to I plus minus I integral minus infinity to infinity dt1 H hat interaction T1 I which is equal to, so I have 1 minus I integral minus infinity to infinity dt1 H hat I T1 acting on the initial state. So this is equal to, this is supposed to equal the S matrix operator acting on the initial state. So what we have is the S matrix operator. We've got the first order term. There is also, there will be higher order corrections that we're going to do later on. But just working to first order, first term, so if we, as I said, if we substituted this into the right-hand side here, then we'll get second order terms, third order terms, so we'll get an iteration. So there are extra terms here in the expression for S, but we're just working the first order. So our S matrix operator is equal to 1 plus a first order correction, where the first order correction is just this here, minus I integral from minus infinity to infinity, and we can just write it t1, we can just write it dt, h hat interaction at time t. And now, all right, so now, what is our interaction? So let's leave off the t. We know it's a function of time. Our interaction Hamiltonian is an integral over a Hamiltonian density. So I can write this as minus I times the integral, a space-time integral. Okay, I've just put that the interaction Hamiltonian is the integral over all space of the interaction Hamiltonian density. Okay, so my time integral becomes an integral over time with an integral over space. In other words, I have an integral over space-time. So now, if you now look back in your notes and find out, well, what is our interaction Hamiltonian density in terms of psi and A, in terms of our field operators, we have the following, you should get the following expression, that we have IE times the integral over space-time of the normal product of psi bar gamma mu A mu psi, where these are operators. So we have an expression, the first order term, hang on, let me just say, the first order term in the S matrix operator is IE integral over space-time normal product psi bar gamma mu A mu psi. Okay, sorry, you had a question?
Yeah, so why the time integral can be transformed into a space-time integral?
Sorry?
The time integral dt, why it can be transformed into dx?
Okay, so what we've done, so we have an integral over time of the interaction Hamiltonian. Okay. Now, the interaction Hamiltonian can be written as an integral over space of the interaction Hamiltonian density. Okay? So this is then just a time and a space integral. So I then have this here. Okay? All right. So now, what we have, let's do 5 minutes. I'm going to show you how the magic works now. Remember, the amplitude, so the probability for transition to an initial to a final state is given by the square of these S matrix elements. So here now, there is a question. We have the following. We have, let me write it out here. First order, to first order, the so the S matrix operator is a series of terms. The zeroth order term is just 1, and then we've got the first order term, the second order term, the third order term. We will look at these later. We're just looking at the first order term. The first order term, let me write it out here again. i.e. integral over space-time of the normal product psi bar gamma mu a mu psi hat. Now, let's think. Remember what we said. The field operators can be written in terms of the expansions that we've used already. So psi can be written as a sum of terms involving C and D dagger. Okay, just symbolically writing the expansion for the Dirac field is a sum over plane waves with C and D dagger. C is the annihilation operator for an electron, D is the creation operator for the positron. The A mu is a sum of A plus A dagger, creation and annihilation operators for photons. Psi bar is a sum over C hat dagger plus D hat. Okay, where C dagger creates electrons and D annihilates positrons. Okay, so now here's where it all begins here. So what are the non-zero matrix elements? This is the question. So, let me just give you one quick example, and then we'll carry on Thursday. So, what are the non-zero matrix elements? So, example. So, 1 contains factors of the form. It contains various kinds of factors, but one factor, it will contain, if I insert the expansions in terms of plane waves and multiply everything out, I will find some factors where I've got a C dagger, and I've got an A and a C. Okay? And what does this do? This kind of term, if I have an initial state, just writing symbolically, we'll do it more precisely later. If I have an initial state that contains an electron and a photon, and if I have a final state that contains just an electron, then if I take the matrix element between the initial and final state, here I have a final state that's just an electron. The matrix, the S matrix operator has a term of this form, C dagger AC. It acts on the initial state, which is an electron together with a photon. If you think about this, and now here's the crucial part, this is not zero, because the annihilation operator can annihilate the electron, this will annihilate the photon, so in other words, I will get A hat, C hat, electron, photon, is just the ground state, okay? Then I will get, this term will create an electron, and I'll get a state with one electron, and so the inner product with this state is not zero. Okay? So think about this. think about this, make sure you understand this, because this is now the key point of how the whole theory is going to work. This term here, symbolically, is written...
Exam next.
Oh, you have an exam? Okay.
Good.
So let me just clean up here. Symbolically, is written like this. With time moving from left to right, I have an initial state that consists of an electron and a photon, and then I have a final state that consists just of an electron. This process corresponds to an electron absorbing a photon. Okay? There are many other kinds of processes in when you multiply out these terms, there are lots of other terms where an electron emits a photon, where an electron and a positron annihilate to form a photon. We'll go over those next time. But just think about this logic, how if I have a certain term that annihilates the particles in the initial state and then creates the particle in the final state, the matrix element is not zero. And in this particular example with this factor here, it corresponds to an electron absorbing a photon. So think about that, and we'll carry on where we left off next time. If there are any questions, please see me after class, and we'll continue on Thursday.